Yeah, so the motivation for this work is basically introduction of closed type families in Haskell, recent implementation of PhD. I just wanted to see how do they handle it? What can we do with them? So how do they compare to what we would usually do with type classes in Haskell? How do they interact? I actually want to provide some code. And I want to apply this to particularly to data from Carte, specifically to the subtyping constraint that we find there, which is the cornerstone of one of the cornerstones of data from Carte. And so the question I was asking myself is, well, this subtyping constraint is implemented using type classes, and thereby it comes with a set of restrictions because of that. And I was wondering, can we get rid of some of the restrictions? Can we improve maybe some of the errors? There won't be a clear yes/no answer here, but so there is some trade-off. There's some trade-offs involved. And so, what price do we have to pay if we enter into this world of type-level programming? So, what is data type like Carte? This morning, Bruno already gave you an overview of that, so I will go through this very quickly. So the idea is to decompose a recursive data type into a two-level type. So we take a recursive data type, such as this representation of expressions with initial and addition, and we turn this into a functor, or we remove the recursion and turn it into a variable, becomes a functor, and then we take a fixed point to get the original data type again. Define this fixed point. The nice thing about these functor representation is that we can combine these functors using a coproduct. For example, if we want to add multiplication, say, to our expression language, we can simply say, well, we take the original functor arith and add multiplication and take a fixed point of that. So we get an expression language that has also the multiplication function. And again, we can find this coproduct very easily. Now, in order to make this work smoothly, then I can't also comes with this subtyping, which says that functor f is somehow contained in the functor g. For example, what we want to have is that the functor mul should be contained or should be subsumed by the functor arith mul. It occurs here as a sum. The idea is that we want to have, along with this type class, some operations that allows us to go from the smaller value f of a to the bigger value g of a, so inject it into the bigger function. And also the other way around, where we can do some kind of type safe time casting, where we go from the bigger one potentially into the smaller one or nothing. For example, using this machinery, we can find smart constructors for addition, where we say, well, the addition operator works for any type over functor f, where the f at least contains arithmetic. And we can do this for all the other constructors, and we can use them to build expressions over combined signature using a mul and using these injection functions that come with this type class. But because it's a type class in Haskell, it comes with a set of limitations. So this is maybe something that how we would actually define the instance declaration for this type. We would say, well, this subtyping has to be reflexive, so f is subtyping, and it lives over sum. So if we have f smaller than f1, then also it's smaller than f1 plus something else. And symmetrically, also it would have f smaller than f2, then also something smaller than something, and then f2. Actually, you can't write this like as it is here, because you essentially define the same instance. It's exactly the same. It only differs in the context that you give here. So, in order for Haskell to be able to accept that and do something with it, it would have to do some backtracking search to find the right instances. So what it's actually done is we have to pick one of those rules, and for the other one we take a particular instance F1 actually has to be this F here. We actually don't look into the structure of this F here. So this is rather, we treat classes here rather asymmetric. So there's this co-product we treat asymmetric, so that we have, for example, that A is contained in A plus B plus C with a parenthesis like this, but it is not the case if we put the parenthesis like that. So that's why you usually say, well, we only want to emphasize these to the right. But this also does not work because we actually also don't inspect the left-hand side. So here we only have this F. We don't check whether this is the sum itself, which means that if we have A plus B is in, we have this subtype of A plus B plus C, parentheses like that. But if you put the parentheses like that, then we don't have it anymore. So this is somehow counterintuitive for me, I think. And thirdly, we also get instances that we actually, or maybe don't want to have. For example, this one here, where we have ambiguity. Where we have that A is in A plus B. And the problem with that is that we automatically derive these injections, right? And if we only look at the type, we don't know, well, which one do we mean? Do we mean the injection that injects the A into this, onto this component? So we also want to rather avoid this. So what we did is we re-implemented this constraint, this subtype constraint, using closed type families, so that subtyping behaves as you would intuitively expect. I'll come to that in the next slide. In particular, we want to avoid these ambiguities in the way we derive these injections. And moreover, because we are able in this way to exhaustively capture this notion of subtyping, we can use that to also express type isomorphism, which then allows us also to actually not only compose these types, but also to decompose. Okay. So what do I mean by subtyping behaves as expected? So what we want is that if F is smaller than G, then there has to be a unique injection from F to G, in the sense that, well, we can map every component here uniquely to a component here. C, this C, A, this A. And it has to be injected. So in particular, we want to reject the following. We want to reject this one because there's no unique injection. But map this A to this or to this. So we want to reject this. We want also to reject these kind of subtypes because an injection function would actually not be objective at all because it would map both this A and this A. So we also reject that. So that works. And because we're able to accurately capture this subtyping, we can also express isomorphism. The meaning of this should be that, well, F and G are isomorphic, there's a unique rejection. That is simply defined as a subtyping in either direction. So F is smaller than G and G is smaller than F. And the use case for that is, for example, a richer form of projection. So the subtyping comes with this projection function as illustrated on the earlier slide. So which says that I can go from the bigger type to the smaller one, but maybe not. And the problem is, well, if we get the nothing case, so in case this function returns nothing, we actually know something. We know that the value, the original value, is in this G, but only in the part of G that is not in A. That is not in F. But it's not. This is not expressed by this type. But the isomorphism, we can express that. So instead of saying F is smaller than G, we can say, well, G can be decomposed into F and some rest, some remainder, so that we can decompose value G of A into some consisting of F of A or R. And this allows us to define a dimension combinator, which we would maybe define like this. So we take the value of G of A, and then we can give two functions which consider the two cases, either as F of A or R of A. So we can define some pattern.
So if you rule out ambiguous subtyping constraints, that also means you have to sacrifice reflexivity as well. Don't you? So A plus A, it can't be a subtype of A plus A.
Yes, we have to sacrifice it. Yes, that's true.
Okay.
I come to that what this actually means. So there's the question of granularity, right? You never look into an atomic, whatever that actually means, atomic functor. You only consider the structure of the pluses when you look at that. Okay, so let's look at the implementation of how do we actually implement this using closed type level. And the idea is fairly simple. So we define a type level function and that using closed type level. And it takes two signatures as arguments, F and G, and it simply checks. It can go over the structure and check whether F should be smaller than G. Then the question comes, well, this all should happen at the type level. What do we do at the term level? How do we actually get the functions injection and projection that we have in the original type class definition? And again, the solution is standard. Instead of just checking this subtyping, we produce a proof object that proves this, that F is smaller than G. And using this proof object, we derive these methods, image and projection. So we still use a type class, but we use these proof objects that we get here as an oracle that somehow guides the search through the instances. Through the instance declarations. So this all happens at compile times. There's no singleton types, so this runs as efficient as the original implementation. And to simplify the matter a bit, I will actually not produce proof objects for this F smaller than G, but in fact for something that I call smaller G. So it's somehow a lax version of this one, in which we allow ambiguity just for the sake of making these proof objects simpler, so we can easily define these injection objects. And then after that, we have a predicate that checks whether these proofs actually proofs for the relation we want. That simplifies that. So how do these proof objects look like? They're very simple. We have reflection. We have lifting to the left of the sum, to the right of the sum, and also lifting two proofs over a complete sum. So just to be sure what this means. So reflexivity means, well, F is smaller than F. And the left and right mean that if we have a proof of F smaller than G1, then we lift that to a proof of F is smaller than G1 plus something else. And this is symmetric. So we have F smaller than G2, and we lift it to F smaller than something else. And the sum lifts it on the left of the smaller than. So we have two proofs for F1 smaller than G, and we have 2 smaller than G, and we have the sum of 2 smaller than G. And this we lift to the kite level. So we use data type promotion to move this data type to the kite level such that this becomes a type, this becomes a type. So we can actually do these type computation, type level computation. Okay, so how do we do this? So now we actually see some closed type elements in action. So this is the return type of the closed type element. So we have these proof objects here, and this marks them as okay, we found some proof objects. And here we say, well, we did not find anything, and here we already found some ambiguity. And the type element we define looks like this. So we declare the type element embed. It takes these two functors, F and G, of this kind, and then it returns this result type, this embedding, which either is a success, it's a proof object, or some error. Either we did not find any embedding, we don't want to return the embedding we found because it's ambiguous. Okay. These are the equations. So we can actually do some kind of form of data animation. And they are a bit more general in some sense than the parametering you're used to on the terminal, because it can actually be nonlinear. So you can say, well, if we embed two functors and they're actually the same, then we use the reflexivity. So here we check whether we can decompose the first one to a sum, and if so, we check separately the individual sums of the sum against the right-hand side of the equation. And then if they are successful, we combine them using the sum constructor. And this is where some of the backtracking happens, where we go to check whether we actually find embedding into the right-hand side of the sum, so f into g or f into g2. So we use this choose family, which is defined separately. Here we already discover some ambiguity. So, for example, if we find an embedding for both sides, so then we know that the result is can find a unique embedding. So we know that it's current ambiguous. And for these two cases, here we simply propagate whenever we already found something ambiguous in one of the two cases. The unsuccessful ones are if we only find an embedding proof object on the left, or if we find one on the right, then we use the proper proof constructor left. In other cases, we use the different modifier. And this is the catch-all case that simply say.
So returning to Jeremy's point, because of the way you order the equations, it seems like you will have A plus A subtype A plus A because the reflexivity is the first equation.
Yes, we have to resolve that.
Oh, so it will fail later.
It will fail later. Yes, that's the idea. So there's several approaches to this, and the easiest one is actually turning this around, because it is simpler to do the actual checking afterwards on this kind rather than on the kind of star. So technically, it would be better here to turn it around for the implementation.
Doctor, can you just quickly show me the data type proof again? Okay. So the record is not forcing anything to be done.
Okay, so this is almost what we want. So we already get rid of some of the reflexivity. Not reflexivity. It's all the ambiguity where we avoid these kind of ambiguous situations. But we do not avoid ambiguities of this form, where we find something that is a sum and it is contained, it occurs twice here. So, but the solution is rather simple. So we simply take the proof object that we found and look for these kind of patterns where, for example, here that we have the proof object look like this, that we have 2 times the pointers. So this A points to this A, and this A also points to this A. With both the left and right, or the left points both. So that way we get rid of these ambiguities. Okay, so we constructed these proof objects. We check whether they follow our restricted forms of subtyping, and what remains is deriving these injections and projections. So this is a rather awkward formatting of the original instance declarations for ADS1. And you see there's some holes in there. I will fill in a second. And the idea is to add the cases that we want. So this is the weird case where we treat the plus asymmetric. We make it so that it's symmetric to the case for the left hand side, and for the right hand side. And then we also add a case that also looks at the left hand side of the rest. The problem is it comes like this does not work, right? Because we would need, for example, here, because we have 2 instances declarations that are the same. So this wouldn't work. So the idea is to add an additional argument. To do that, we turn this binary class into a ternary class. We write a prefix. So it gets this additional embedding argument, which will act as the orgle, which guides the instance declaration. So we add the proper proof terms here, which are essentially the same as we've seen on the previous slides, is these proof rules. And this then works. So we only have to write the proper functions in the application. They are as in the original implementation. Okay, and then we can define the subtyping, so epsilon and G simply as, well, epsilon and G, or we add this embedding. So that's the actual work. So this actually does the search and looking whether we have this subtyping, and then adds this as a order as the first line. Okay, that already brings me to the last slide. So this is a general technique that is also applicable to similar problem domains where you have some kind of search space you want to go through, and then you want to be able to derive code for that. And you can simply do this on a type level and give that as an argument to the type class to guide the search. And in this particular case, it improves many of the, or some aspects of the original implementation, so that we rule out certain things that we don't want to have and make this more general. However, there are some caveats. Error messages are tricky. The problem is that that the simplification of closed type families may get stuck. And the problem is that you get this stuck term with some intermediate terms that you have no idea what they mean because they are part of the internal workings of the implementation. You just get them in your face in the error message, and you have no idea what they mean. I think that's the biggest problem. And I think this should be solvable. I mean, you just have to some kind of domain-specific knowledge about the implementation, how to read these, or how to reformat these in terms of the external interface. And I also found some very weird performance issues where type checking just took way longer than it should, or than I thought it should. You can get around it, but you have to do some kind of type level profiling, which is entirely all right, so I implemented this. This is available as part of the composition data type package. So if you are willing to experiment with this as well, you can install it, and with that I'll take a look at this.
So before I open the floor to questions, I've been asked to kick off the discussion. So thank you, Patrick, for your paper. And what I like about it is a nice example of kind of modern type-level programming action. And because there's an existing problem figuring out injections into subject code, which has already been done using type classes, it's quite nice to see it kind of compare to how you would write solve the same problem using closed type classes. So in the original data types on the Carte, one of the big problems is figuring out the right injections. And it uses a cheap trick, which is that if you do a kind of logic programming style, you can piggyback on the class inference or instance inference search that's already supported by Haskell as you search for the right summon of the code. So it's cheap, but it's limited, and there are a lot of drawbacks to you named which you mentioned in your talk. And people have thought about this, and I've seen other solutions by Oleg, Caselio, and by Ingram, who kind of did the same stuff you're doing, but then they code with a type class, which is probably not as nice. The good news is, what I like about data types on the Carte is it has a pretty good power to rate ratio, right? You need 3 instances to describe the search, and then that's it. You pull off a lot more. You get a lot of expressive power. You can also have much more flexibility in choosing, do I allow ambiguous constraints or not? Or how the search proceeds. do a much better job. The price is that you do a lot more type-level programming. And you get a lot of complication. So one question is, where does that complication come from? On the one hand, you might say, well, there's no type-level programming. If you read the full paper, there's lots of things where you have to, build up booleans, and it'd be nicer if there was more support. But I think crucially here is that there's no built-in search. So one question you can start asking yourself is, what can we do to make this kind of thing easier or reusable? Is there a way to specify the search which hasn't been trying to resolve instances using closed type families, or at least a fragment? And if you have such a generic type of search algorithm that you make instantiate this can kind of present a simple kind of symmetric definition, and then which piggybacks on a big library. And of course, it's interesting to see what kind of problems you run into with compile type. So these are a few thoughts which I wanted to share. Thank you for your paper, and I'd like to open up for questions. Leonard.
So it's not so much a question as a comment. So the error messages, I have a solution to that, but you have to convince GHC people to implement it. I've implemented it in our Haskell compiler. So it's basically the same as you have on the term level. You have an error function. You can have an error function on the type level, and you give it the string literal and some other things. And when the type checker sees that, it prints that in a sort of special way, and you can get a lot of lot nicer error messages that way.
Yeah, the problem is that it's not really in your hand when the term gets stuck somehow. There's no, at least as far as I know, you don't know it. So
but that's kind of the same as when it happens on the term level. You might not want to display the things that you had right when you got.
Yeah.
But when something went wrong, you have to pass the original parameters along down to the point where you can generate the error message. So it's a bit messy, but you can produce nice error messages.
I mean, what I've seen is what I think is a nice idea is to provide some kind of reflection of the for the type errors that you get. I think that I've seen it in Idris that they're doing that. It's very nice that you can basically take the error message as the user would see it, and then see recognize some kind of pattern in there, and then translate it into a human readable form. So I think that would be a more general way of solving this issue.
And also much more difficult to implement.
It wasn't that bad.
First, actually, I wanted to comment to you. So we had this approach in HList. It's called a TopClass Fail that doesn't have any instances, and one of the parameters that's like a type that just encodes the error message. But I think I know what what his problem is. That before he actually gets to fail, he needs to know that it fails a particular way. And there is a way to do this. And I had this problem. If you want to know how search proceeds, because the problem is that you don't know which constraint GHC handles first. And there is only easy ways to do it. You just CPS your type level program, and then you make the order deterministic. And in that case, you know exactly where you fail, and that's where you give the error message. So it's actually doable. So, but my question, remark to you is your restriction that you said, you A plus A, you don't restrict. So if you look at it, so you want to, your problem is, or the problem you're trying to solve is that you have what's called type indexed record, right? So, which were existed, introduced, in the last century, I think. And what you are checking is the inclusion of subtyping or inclusion of two type indexed records, right? So, and that has been indeed implemented, including injection and projection. So if you think about put the problem in this way, type indexed record, then of course you need to add the constraint that it is a record, then it's all the types are unique, and of course, that can be done. And so the problem becomes to just provide the inclusion of the type index, or check the inclusion of type index record. And that's relatively, has been done. So the only thing, of course, the new compiler does is that, before we all did tricks with overlapping instances because we need type level quality, and closed type instances give us type level quality for free. So that was a crucial part which was missing back then, right? So I think that if you put the problem this way, then it becomes much easier and then relates to the work from the last century.
Slightly different. So I suppose the motivation for what you're doing here is sort of switching from the data types a la carte model of generic data types as co-products of products to sums of products. So in other words, discarding something sort of order in a co-product type.
Yes.
I suppose my question is, I'm actually recently discovering some actually really nice interesting properties you get from thinking actually in terms of co-products and products just in their own right. I'm kind of wondering whether you think there's an interesting trade-off to be made between these two views.
Between what?
Well, between a representation of generic types as co-products, products, which obviously this includes additional types that you're excluding by focusing on some products. Do you think that's? Are you giving anything up here that might actually be useful?
I think anything.
Well, there are some types that you're excluding. I mean, that's what your second constraint is doing when you're clarifying those.
You can just do renaming, right? You can just produce isomorphic copies. That's the idea that you want to make it explicit in the typing, that you want to see from the types what the semantics is instead of guessing what the semantics will be, because you choose something arbitrarily from the different choices. So in that sense, I don't hear up anything, but I want to make it explicit. So I assume that anything else would be a program error. Maybe it's not, but then the programmer has to make that explicit.
So first off, it'd be great to get test cases that show that weird compiler behavior, because maybe we can address that. So if you have those still around,
Yes, I know it's called, of course.
So the other thing is, I don't know how familiar you are with instance chains. How, if that were implemented in GHC, would that have solved the problem? Because what it looks like you were doing is, you can basically implement instance chain through closed type families with exactly this trick.
Yes. Okay. Yes, that would solve the problem. Yes. I mean, in general, just make the search for instances more flexible in the sense of already backtracking. If we put backtracking, then it would already be sufficient.
So all this type hackery is a way of getting the injections and projections. And I wonder, it just occurs to me whether it would be easier to just provide those explicitly rather than try and infer them, and what they amount to in the lens from the wider type to the narrow one. You want to be able to view where the narrow one is in the context of the wider one.
Yeah, of course you can do that, but often it's just inconvenient. It's sort of the idea is that it's obvious which injection do you mean, because it's obvious from the type. If I have an integer and I have a sum of an integer and a bool, and I want to put one into the other, then it should be obvious which one I mean. So that's the idea. But in other cases, you want to do something different, right? And then you want to rather have lenses and want to combine them and be more flexible. This is a different setup.
So do you really think it's just pragmatically less convenient to?
No, it's two different use cases. I think that there's use for both approaches. I'm just looking at one of them. Which,
one last question.
It seems to me that oftentimes you might construct something using a bunch of injections and then want to destruct using a bunch of projections. And even though there is a choice of a particular ordering of sums which would be able to satisfy this, there's no canonical choice, because you could order them however you want. If I want to inject an integer and then a Boolean, then project out an integer and a Boolean, I could just choose integer plus Boolean. But you're going to run into ambiguity errors unless you annotate that middle type in there somewhere.
yes, that is a problem. That you need to know what is the input and what is the output type. So that is indeed a problem.
And like, despite there being some minimal and arbitrary, a minimal but arbitrary choice of that intermediate type, there's no current way for us to actually make that choice automatically.
Exactly. Yeah. That is a problem, and is also currently very, very hard to deal with because the error messages are not very, very helpful. Yes, that's correct.
Okay, let's take one last time.